right, the next thing I want to talk about is some basic properties of logs. Now these are given in your text and they're given with the answers, but we actually have the tools to figure these out. So I want to see if we can't figure each one of these out. So the first one says the log base b of 1 is equal to what? So I'm going to do my usual trick of just giving that a name, and then I can rearrange things into exponential form. So this says the exponent I need when b is the base. To get 1, exponent is x, and we're trying to figure out what x is, what goes here. I don't know what the base is, but I should be able to figure out what power is going to give me 1. That's because anything to the 0 power is always 1. Okay. So the log of 1 will always be 0. It does not matter what the base is. Just like base b to the 0 is always 1, the log of base b of 1 is always 0. Okay, excellent. Let's try the next one. So this says the log base b of b is what? I'm going to give that a name, and we're going to try to figure out what x is. And it's generally easier to see once we've rewritten it in exponential form. Some of these you might be able to see while things are still in logarithmic form, particularly as we work with logs a little bit more and you get more comfortable with them. You may find that rewriting things in exponential form isn't necessary every single time. But it's really useful and it generally makes things easier. So if you never get to the point where you're not rewriting things in exponential form, I'm fine with that. Because if you're doing this, you're understanding what this means rather than just memorizing a bunch of facts. Okay. All right, so this says the exponent I need when b is the base to get b. b is also the result. What's that exponent? Well, I'm thinking that should be 1. Because whatever I have, when I take it to the first, I just get what I had. So if the argument and the base are the same, the log or the exponent is 1. Okay. Now, these next two look a lot more complicated. I'm going to work them out this same way, but then I'm going to also show you another way of thinking about them. Okay. So, here we've got the log base b of b to the x. Now, I might just put that in parentheses, just to make it clear that that's what's in the argument position. And I'm going to give that a name. Now, obviously, I can't call that x because that symbol is already taken. So I'm just going to call that y, and we'll see if we can't figure that out. Okay. So we would have a base, we would have an exponent, and we would have a result. So this says the exponent I need when b is the base. To get b to the x, that's the result. That exponent is y, and we're now trying to figure out what is y. I want to simplify that. So we're saying, well, b to what power would give me b to the x? That would be x. This is saying, what's the exponent I need when b is my base to get b raised to the x? Well, that exponent is x. Now, I wasn't allowed to call it x until I knew that was the right answer. I couldn't assign x as a variable name for an unknown when x was already in the problem. But it turns out that's what it simplifies to. Okay. Now, this last one is a little bit different because we're not just evaluating a log, we're evaluating b to a log. Well, that kind of makes sense because log means exponent, so we're evaluating b to an exponent. I'm going to just write out that exponent. The log base b of x, I'm going to just give that a simpler name. I'm going to call that y, okay, so that I can say that b to the log base b of x is the same as b to the y. I've just given it a nickname. Okay. And now I'm going to rewrite this equation in exponential form. Exponent I need when b is the base to get x is y. Oh, that tells me what b to the y is. B to the y is x. Now, these last two, I said there was another way of looking at them. Both of these are the composition of two inverse functions. Okay. Here, if I were to say f of x was the exponential function b to the x, then f inverse of x would just be the log function with that same base. So it would be the log base b of x. Okay. So if I look at this, that's taking b to the x, which is f of x, and plugging it in to the log function. So that's f inverse of f of x is just x. We took x, we plugged it into the exponential function. Then we undid that by plugging into the log function. Okay. People will often talk about an exponential function and a log function canceling. I'm not crazy about that word because canceling makes me think something more arithmetic. Like if I add 2 and I subtract 2, a plus 2 and a minus 2 cancel each other out. If I multiply by 3 and I divide by 3, they cancel each other out. I prefer to use the words these undo each other. The log function undoes the exponentiation. Okay. As if you don't start thinking of it as multiplication and you use the word cancel, I'm not going to tell you that's absolutely horrid and wrong. But if the word cancel is associated in your mind with arithmetic operations, don't use it. Better to just say, hey, log functions undo exponential functions. Now, this is an exponential function undoing a log function. Notice what we're doing is we're taking the log base b of x, that was our f inverse of x, and we're plugging it in to the exponential function. So this is just f of f inverse of x is equal to x. So these two compositions are just a log function and an exponential function with the same base being composed, and they're going to undo each other, and so they give you back just x. All right. So let's just practice a little bit, because these things look a lot more complicated than they are. Let's say I had the log of 10 to the 5th. Well, that's the exponential function with a base of 10 being plugged into the common log, which is the log function with the base of 10. So the log function is going to undo the exponential function, and I'm just going to have 5. Okay. Let's take e to the natural log of 3. Well, that's a log function, and it's the natural log, so it's base e. So that's the natural log being plugged into the exponential function with the same base. They're going to undo each other, and that's going to just give me back 3. Okay. I want to just show you something else. I don't think the book actually has any examples this challenging, but it's kind of cool, and you will encounter this as you move your way through calculus. If I have e to the 2 times the natural log of 3, okay. Need to be careful here. I see a log and I see an exponential function with the same base. So I want to see some stuff being undone here, but I've also got this 2 here. Notice the log and the exponential function aren't directly next to each other the way they are right here. But notice, this is the same as e to the natural log of 3 times 2. Now, I'm not multiplying 3 times 2. I'm multiplying the natural log of 3 by 2, because that's what we're doing. The natural log of 3 is just some number. 2 is some other number, and I'm multiplying those two together. Remember, when we're multiplying in the exponent position, I can view that as a power to a power. So that's e to the natural log of 3, that quantity squared. Cool. E to the natural log of 3, that's me plugging the natural log function into the natural exponential function. They undo each other. So that's 3. I'm still squaring it. 3 squared would give me 9. Okay. All right, so those are some really important properties of logs. These two, again, really just, even though they look very complicated, they're just saying what we've been saying this entire section. A log function base b is the inverse of an exponential function base b. And so if you compose them in either order, they're going to undo each other and give you back what you started with.